Geothermal versus other renewables. Our planet faces an undeniable challenge: climate change. The urgent need to decarbonize our energy systems has spurred an incredible global acceleration in renewable energy deployment. From the sun-drenched plains to the blustery coasts, and even deep beneath our feet, humanity is harnessing nature's power. But as we rapidly build this new energy future, it's critical to ask, what role does each renewable play? And where does geothermal energy truly shine in this diverse landscape? Solar photovoltaic, or PV, and wind power have seen exponential growth driven by falling costs and technological advancements. Solar panels are remarkably versatile, scalable from rooftops to utility scale plants, offering clean energy directly where it's consumed. Wind energy, particularly from larger, more efficient turbines, is often one of the most cost competitive forms of new electricity generation. However, their fundamental reliance on ambient conditions presents the challenge of intermittency. Solar output directly correlates with sunlight availability, peaking during the day, dropping to zero at night, and fluctuating with cloud cover. Wind power fluctuates with wind speed, meaning production can vary dramatically hour by hour or even minute by minute. Managing this variability requires sophisticated grid management, or more significantly, large-scale energy storage solutions like batteries, which add complexity and cost. This is where geothermal energy emerges as a critical differentiator. Unlike solar and wind, geothermal power taps into the Earth's continuous internal heat. This fundamental difference means geothermal plants can operate around the clock, providing a constant, reliable supply of electricity, a characteristic known as baseload power. Consider the capacity factor, a key metric indicating how often a power plant actually operates at its maximum possible output. While solar and wind typically have capacity factors ranging from 25 to 50%, depending on location and technology, geothermal plants consistently achieve capacity factors of 90% or higher. This exceptionally reliable makes geothermal an invaluable asset for grid stability, reducing the need for fossil fuel peaker plants that typically fill gaps when intermittent renewables aren't producing. Furthermore, the consistent output of geothermal makes it a strong candidate for industrial applications, requiring constant power, and it significantly lowers the complexity of grid integration compared to highly variable sources. When evaluating renewables, their environmental footprint beyond carbon emissions is also crucial. Solar farms, particularly at utility scale, require extensive land for panel arrays. Wind farms, while also having smaller physical footprint per turbine, need large areas for turbine spacing and access roads. This can lead to concerns about habitat fragmentation and visual impact. Geothermal power plants, by contrast, typically have a significantly smaller surface footprint per megawatt of capacity. The bulk of the infrastructure is underground. While geothermal development involves drilling, which can have localized impacts, the overall land disturbance is often less than large-scale solar or wind installations for comparable power output. Regarding emissions, while solar and wind produces virtually zero operational emissions, the manufacturing and the installation processes do have an embodied carbon footprint. Geothermal also boasts a very low operational carbon footprint, drastically lower than fossil fuels. Some geothermal systems can release trace amounts of non-condensable gases, including CO2 or H2S, naturally present in geothermal fluid. However, Modern geothermal plants often employ closed loop binary systems or reinjection technologies that capture and reinject these gases, minimizing atmospheric release and demonstrating a path towards near zero emissions. Economically, the renewable landscape is dynamic. Solar and wind have seen dramatic reduction in their levelized cost of electricity, or LCOE, making them highly competitive. However, these LCOE calculations often don't fully internalize the costs of grid modernization, transmission upgrades, and large scale battery storage necessary to accommodate their intermittency. Geothermal projects typically have a higher upfront capital cost due to the need for extensive geological exploration and deep drilling, which can be expensive and carry geological risk. However, once operational, geothermal plants have very low and stable operating and maintenance costs and are less susceptible to fuel price volatility and boast exceptionally long operational lifespans, often 30 years or more, frequently extending to 50 years with proper management. This provides long-term energy security and a predictable cost trajectory. While the global potential for geothermal energy is vast, its commercially viable deployment has historically been geographically constrained to regions with naturally occurring high temperatures resources, often along tectonic plate boundaries like the Ring of Fire or rift zones. This contrasts with solar and wind, which are deployable across much wider geographies. However, this constraint is rapidly evolving with the advent of enhanced geothermal systems, or EGS, as we learned earlier. EGS technology aims to unlock vast, previously inaccessible geothermal resources by creating engineered reservoirs in hot, dry rock formations. This involves injecting water at high pressure to create or enhance fractures, allowing water to circulate and extract heat, mimicking natural geothermal systems. EGS represents a paradigm shift, potentially expanding geothermal's deployability footprint to virtually any location with sufficient heat and depth, transforming it into a truly global energy solution. In the grand symphony of renewable energy, each instrument plays a vital part. Solar and wind offer rapidly deployable, increasingly cost effective solutions for widespread electrification. But geothermal, with its unparalleled baseload capacity, compact footprint, and unwavering reliability, provides the foundational rhythm, the steady, always on power that underpins a truly resilient and sustainable energy grid. The future of energy is not a single source, but a diversified, intelligent mix, where geothermal takes its rightful place as an indispensable pillar of our clean energy transition.